Hello everybody for being here today for this seminar. It's my pleasure to introduce José Proença for his talk on interaction-based paradigm. We have witnessed the programming paradigm on single core, sequential, the one on multi-core, which is parallel. And now today I think we will address those questions mostly from a formal viewpoint, to put some formalism in these things. So, José, if you work on José, he did his PhD from the Netherlands.
I have a slide for that.
Okay, so perfect. And he's a little bit globetrotter as I am. So after working in the Netherlands, he went to Brussels to
Leuven.
Leuven. And later he got the call by the home country, and then he came back to Portugal. And we are very, very pleased to have him in the team, and I hope this will trigger a lot of collaboration. Please have this talk be very interactive. I guess that this is what he's looking for, and I hope you are going to have a lot of fun with us.
Okay, thank you. Yeah, thank you for your Patrick. So, I'm José Proença. I started working here recently. It was the beginning of February, even though the first month I was completely away because of the newborn child. I come from a background where I do more formal methods, higher level specification. So, in these slides, first I'm going to talk about my background in one slide, and then I'm going to choose a topic that is more common, and I'll focus reusing slides from teaching. And only in the end, I'll give you a glimpse of current interaction I'm actually investigating nowadays. So, this is my background. It was around 2005 where I graduated not from here, but from Milan University, it's more in the north. So my background is a bit on mathematics and computer science. Then I defended my PhD in the Netherlands. I was working in Amsterdam in a research institute called CWI. And there, my background was mainly working on coordination with Professor Farhad Arbab. But here, so they have a strong background on software engineering, but also some formal methods, concurrency theory, and so forth. So it's a higher level. It's a way of specifying how things communicate with each other. From application level and less from implementation engineering perspective. So most of my talk will actually emphasize on this coordination aspect. What is coordination for me? And I'll talk a bit more about this during this lecture. After that, I went to work in Belgium, later in ESCTech in Prague again. The topics also include this coordination field, this concurrency. I'm just emphasizing the new things that I start working in. So when I went to Belgium, to Leuven, so it's around 50 minutes drive from Brussels, I start investing more on programming languages and also in the notion of variability. So what happens if your system have multiple ways of compiling based on your parameters, and you want to reason formally about the parameters and impact on your system. And I also worked at some point, so first with Dave Clark, he comes also from type systems community and so forth. And later I went to work with Danny Hughes, who was leading the team on the wireless sensor networks. And there I also exploited the idea of reactive programming. So I started formalizing and understanding the component-based system that we were developing using there in Belgium. So when I went to Prague, I focused more on process calculi, software architecture, so for a more mathematical approach to describe this. But still, again, never losing track of this coordination track, which I'm still investing. And at some point, I start working here. So my door is always open as well. If there's anything you find that might be useful discussing, please don't hesitate to just open the door, knock and enter. I'm on the second floor, close to the cafeteria, old office of Patrick. So this is the background. By the way, this talk is supposed to be interactive. I have no problem interrupting whatsoever during the talk. So, outline. Let's see some more content. So in this talk, I'm going to focus on this idea of coordination. because I worked a lot and I still push me a bit this in my research track. I'll spend quite a long time just talking about context and motivation. Why do you want to talk about coordination? What is it good for? And I'll focus on this language called real coordination language, which is something visual. This is a connector, it's a program, or a communication protocol in the real. So I'll spend quite a lot of my talk talking about this, and it's actually something I also taught my students, so I'm using some slides. And then in the end I have something like 4 to 6 slides just talking about current research tracks, mainly about how do you look at timed automata, that most of you are probably already heard, and start adding new things to make it more interesting. And also a current project that I'm leading now that involves a company doing real-time operating systems. They have their own real-time operating system, and we're trying to investigate ways of improving the way of talking about constraints between tasks. So this work that is submitted but not published yet, we're still waiting for the reply. So these are examples of tracks that I'm going to try to explain. So coordination, context and motivation. So the context is reactive systems. So if you have a reactive system, so several pieces that try to communicate with each other, how do we design a context system that actually combines these? So we have components, services, processes, tasks, whatever you want to call them, and they all you want to combine them and compose them, assembling some kind of architecture. How do you specify that architecture? How do you develop in a way that you can easily analyze it, configure, understand what it is? So how do you increase understanding of how they are combined? The moment you don't have only 2 or 3, but you actually have 10, 20 or more. So in the literature, this is quite well studied, the topic in the area of concurrency. So there are several models that handle concurrency. You might have heard a few of these. So there are Petri nets that are very good at modeling resources. There are some diagrams for workflow and data flow. You also have some process algebra or calculi, a way of specifying what the process does in a very compact representation to make sure you can actually reason about it more properly. There are also the agents community actor models as a way of specifying how actors or how entities can send messages asynchronously. But in all these models, interaction between them appears very implicit. And what I mean by implicit, so I'm going to have a bunch more slides to emphasize what implicit means. But basically, you specify inside each actor, inside each entity, how they communicate with a specific partner, and that's where the code is to be able to capture the protocol of communication. And basically, interaction appears as side effect in the sense that when you have someone trying to send and someone trying to receive data, if they happen to be at the same time, they actually communicate. But the actions, the fact that they might or not coincide, it depends on how each of the components actually implemented. So it's usually very hard to specify, verify, manipulate, or even reuse these communication protocols. So this is an example of interaction in process algebra. Because I expect most of you not have a background in process algebra, I have this example with a twist in the next slide, but focusing on code, on Java-based code that's a bit easier to understand. Here the key idea is that if you want to specify or model a system, in this case you have G, R, B, which are processes running, communicating in parallel. At some point G tries to perform an action called G that can only happen if at some point someone performs this G bar. So they have these synchronization mechanisms. So actions are these things trying to act, to do something, but when they are in parallel, they are restricted. They can only continue if there's a partner that tries to do the same one. So if someone looks at this code, you actually struggle to understand what's happening, who is talking to who, and you end up drawing some diagram where you say, here's G, here's R, here's B, and trying to have some message passing around and understand what's happening. So a very similar example, but now using Java. Imagine you have three components running. A producer, red, green, and blue. So in my laptop, this actually looks red. Here it looks a different shade of gray. But assume you have a producer, 2 producers, and a consumer. And they are communicating how? Using shared memory. Shared memory are these shared objects. So this basically sounds like Java. And the key idea is that you have this buffer that you want to use to send the consumer. The consumer reads the buffer and prints it. And these producers somehow update the buffer, but before that, we use this lock, this semaphore. This is basically to avoid race conditions. So we can actually update the content of the buffer without anyone updating it and without him reading it, and only after you release the lock you can use it. So now you see some extra locks here as well. So besides the lock for the buffer, you have the semaphores, which I hope everyone knows what a semaphore is. So in this case, we use the red and the green semaphore somehow to control if the green process of the red process can go. So you look at this code, and there's also something extra. Green text, you can actually find the text that's going to be passed to the buffer. You actually have some sleep involved as well, some time constraints. And then possible questions is, where is the green or the red text computed? Look at the text and oh, it's here. There. And the possible question is, where the text printed? Look at all the code and you find it, okay, it's in this line. But then you start looking at the protocol. So who determines who goes first? You know who goes first in this case? Any suggestion? So I was a bit brief over here. So what you understand is that you're initializing semaphores here. So it's the way that semaphores are initiated tells you who can acquire the first semaphore first. So you look at, okay, I see there's a 0 there. So the red one cannot start yet. You can compute the data, but actually the green that starts. Okay, now I understand. The green starts. These can also start because the semaphore for the buffer is also available. So basically, by doing this, understand that green, red, red, green are alternating. You analyze a bit further and understand, okay, now I finally understood what's happening. They are alternating. So starts with the green one, the only one can acquire the lock. Once it finishes, it allows the red one to go. The red one goes. After performing this computation, it allows the green one to go, and so forth. So after some point analyzing the code, what you understand is that, oh, I finally understand what's happening. So, and then you draw the diagram. You see, you have the producers 1, the producers 2, and you have this, the consumer. And you understand it's that they are alternating between who goes by sending messages explicitly, and the messages are via this as semaphore. At some point, they send some information to this consumer and says, "Just that data for you to write." Now the question is, where is the code that defines this protocol, alternating and sending data to the consumer? And the answer is spread and tangle through all the processes. So who determines that the producers alternate? There are these two semaphores. What happens if you want to change it? Imagine that you actually want P1 to occur twice, or maybe to have a timeout that actually allows to happen twice or 3 times based on the availability of process 2. And what happens if actually one starts tweaking with these numbers of the sleeps? That might mess up completely your protocol. So this is what the interaction focus paradigm tries to say. We should avoid as much as possible interleaving this protocol-based communication code outside, and is not using the aspects that, like we've seen also in the previous talk, where the alternative they propose is saying, let's put here some mark and saying code before, code after. In a different file, you write this code before and code after, but still the same code. It still requires the programmer to understand exactly what inside this code is in order to program the protocol. So our suggestion is actually to replace this by processing consumers, that the only thing they do is try to send red text to say, I want to write it somewhere, I don't know who is. And for the consumer the same way. I want to receive the data, I'll just print anything that sends to me, but hey, it's like a web service, I'm ready to print text. So you want to replace this by somehow a new entity a connector, a coordinator, something that sits in the middle and defines what the protocol is. So this is this separation of concerns. I think I'm going to slide further. So in this separation of concerns, that for me is very important. Is be able to say, I don't want the code for communication being inside the processes, but I wanted to take it out. And so the key advantage of these things is that we can actually reason much more about this language once it's condensed here, because we can define our own DSLs, our own language. We can focus on the specific semantics. So you have the power to be able to reason about who interacts with who and when. So constraints over who talks to whom, which is very different from looking at the code here. So most of the processes currently still look at the code here, abstract this in something that reflects the same thing but abstracting things away, and then they prove that these systems work. This approach is different. It's saying, no, you should not code this inside. The mind of the programmer should already be focusing and saying two different concerns, computation and coordination should be side by side. So this is the philosophy, the perspective that we try to push. So this slide is meant to say what's the interaction protocol. A protocol is actually a set of possible actions or sequence of actions that you might want to impose. By saying P1 and C communicate at some point at the same time, so they can send data. After that, the only possible thing that can happen is P2 talking to C. So listing somehow a set of intended collisions. And by collisions, I mean this guy trying to send and this trying to receive at the same time. A collision might be actually two people trying to send at the same time and one trying to receive. So it's basically a set of actions trying to trigger multiple actions at the same time, and a sequence of possible ones define what for me interaction protocol is. So how can you reason about this? So that's the focus of this language. So the key idea is that we actually don't want to specify to talk about classes. We talk about more about objects. So we have something running. We have these black box computation units. They compute values somehow. They might use hardware. They might use whatever language you prefer, but you want to be able to connect them using special wires. And these wires specify this communication protocol. And there you can put more or less complex behavior. You can analyze it, you can generate codes, we can do whatever you want to focus on interaction. Okay, so here's this real language, something that was pushed by my PhD supervisor, Farah Rabab, where we try to sell the idea of exogenous coordination. So it's a very fancy name to say the code for coordination is outside the components, not inside. So the opposite will be endogenous coordination, where each of the components know who they are talking to and juggle these to make sure everything works. So push away the coordination, make sure it's compositional, so it's something very important that's trying to push lots of this. So you can have perfectly a script that says first this, then this, then this. But what you want is to make sure you have smaller, reusable connectors that can just keep plugging to each other and be able to build complex systems out of smaller, simpler pieces. So this is something that is being pushed from the beginning. Make sure you can compose things already built before to reuse. Even in software, you have these imports that you need to be able to have a good structure to be able to reuse code. Here, we try to push at the level of just plugging and wiring things that you already had before. So you have this notion of synchronous, but it's like atomicity. So synchronous in the same way as it's called a synchronous method call versus a synchronous method call. Which means that the writer might only succeed if the reader is ready to receive or not, and you call this a single action where both of things happen at the same time. And so, in this perspective, we actually say coordination can be viewed as constraint interaction. So if your key primitive is interactions, how constrain what interactions can be. So here's a small example. So in this example, we have these two producers we saw before. You can have a connection in the middle where you evolve using this real language in steps, in discrete steps. At some point, someone tells the connector, this is what I can do. It can happen that this is ready to write. This says, no, there's no data for me to send. And the consumer says, I'm fully ready to get data. At this point, the connector might be centralized, might be distributed, so there's no restrictions of it's actually running in one place or not. But you will react and say, you can go, you have to wait, and here's some data for you. So this is the kind of reasoning you want to be able to be captured by the connectors. So inside that circle, that blob, that cloud, what you actually see is something drawn like this. So these are screenshots from all the tools that exist. The key idea is that you just draw these kind of arrows. Each of them will impose some kind of constraints. In this case, for example, it says, I'm a synchronizing barrier. Either both of them can go or none of them can go. This one is allowed to buffer some data. The other one is not allowed to buffer data. So basically, you keep plugging these. Each of them have some extra constraints. These nodes are not states. You cannot store the states in those. Are just composing the constraint of each of the pieces. And then now we want to analyze these things. So it's visual, should help somehow with the intuition where data goes. But sometimes it's not that intuitive. That's why I need tools to make this more precise. So lots of text about RIO. So RIO is for interaction protocols. Interaction is the first test concept. So that's what's driven is entities talking to each other. So a program in this case is a connector. So a drawing. It's graphical. Some people will say it's more intuitive. I have some doubts in several cases. It's not as intuitive as one might would like. And then we have formal semantics. So the question is, yeah, I know how to draw this. I know how to draw class and UML diagrams. What does it mean to execute it? What's the semantics behind it? And the point is that we actually have several formal semantics. We'll see a bit later what does it mean to run these things. But we have quite a lot of it. Quite often depends on which primitives you use. If you want to use one that allows you to buffer data, okay, you should know how to talk about buffer data being buffered. Do you want a connector that has a timeout? Okay, then you make sure semantics knows how to do the time. So based on the primitives you choose, you want to filter data based on the data. Okay, your model needs to talk about data. So you adapt and choose the formal semantics you want, and you want to make sure there's some kind of tool support. So right now there's some Eclipse-based tool support, which are not actively maintained, so I'm trying to come up with something more web-based, JavaScript-oriented, just make sure it's easier to reach other people, and we'll see a bit later. So, RIO. Talking a lot about RIO. So RIO basically have, quite often, these are the kind of primitives you see on the literature. You basically have connectors with source and sync ends, saying, I'm ready to receive or ready to send data. And these are examples of possible data. So synchronous method call, only read data if I can write the data to that part. This requires data to be received from both places, and so forth. I'm not going in detail here. Composing is one of the key things in RIO. So you have these connectors. You have this composition operator that says, oh, this B is the same. If B is the same, then composing actually originates that new connector, which can be encapsulated and reused later. And then you need to formalize what this composition is. And this depends on the semantics you actually choose. So you can only plug source to sync ends, one-to-one. If you want to plug more than one together, then you're actually using implicitly this either merging or duplicating behavior. That's implicit every time you connect more than one thing in one node, you're actually using one of these. So these nodes, they are not state, as one might see when they look at the diagram, because everyone knows state machines. But they're actually capturing this pumping station that read and send data in the same step. Right, let me show you an example soon. So this is just to give you a glimpse of kind of semantics that you give to it. So imagine you have this connector. We plug three things together. And now we ask, what's the behavior of this? Well, quite often, this is based on automata. We say, this merger is green. Here's the behavior of the green. And you see the state with two arrows. The two arrows say either A and C can talk to each other, or B and C can talk to each other. So this is one of the most common ways. There are other ways of specifying the behavior. And once you compose these things, you're basically composing the automata of each of them. And then there's a way of building this. So basically, if you want to analyze or even generate code from this, you're not going to deploy these in separate, talking to each other. Typically, you compose the automata first, and then it's far more efficient to actually run this. So this basically makes your connector program a logical representation of what actually happening. And this is very important because lots of people look at this and think, this is not efficient. I'm not going to run this with 10 different things connecting, talking to each other if I can just plug them together. The point is, no, you're allowed to generate efficient code by replacing things by equivalent things. And that's the advantage of being able to shift the pictures into something more formal where actually reason about these things. So I'm not going to formally define this composition, but it's not something very unusual, it's something that's doable.
Are you using the subset construction or variation of that to produce this?
So there are several ways of doing it. So some semantics actually use sets of possible behavior. So this is very similar. So basically what you'll do is look at all possible pairs of transitions and they say, is it compatible? If so, include in the final one. Otherwise, take away. And so you can optimize this construction by making sure you don't compose this with this first, because then you have lots of interleavings, and if you're not careful, the state space can actually explode, even though the final model is small. So there are small things that can actually bite you in the ass in the end, but if you're careful enough, you have experiments, you can actually do it more or less okay. So I'll show now some of the tools soon. So just these two slides saying there are lots of investment done by the time I was doing my PhD in some Eclipse-based framework. It was very popular by those days, 2007, 2008, I think, when it started. So there are lots of different plugins. There was someone who knew how to develop plugins, who had some experience. So there's this EMF, GMF-based way of drawing things, where you drag and drop things. And then you have lots of things that generate 3 or 4 different kinds of automata so you can reason about them. Let's draw it and draw tokens being sent back and forth so you can understand the intuition of the connector. Let's use some outsourcing some object that already exists. So there are tools existing, but they have this small bugs that happen sometimes, and it's not really being maintained right now. So it's something that I would say is slightly deprecated. It's hard to use nowadays. So that's why I'm trying to avoid using this Eclipse plugin. And I'm pushing something that generates JavaScript. So I'm going to open now the browser in a different tab just to show this running. So part of my goal is to be able to open a website, which is already available. So I even have a virtual machine running that actually has this running as a service, where I can write the program using some object constructions, and it draws this automatically. So if I look at the example we had there before, it was a merger. So I'm writing there in the top corner. And then there was something we call the velocity, this dashed connector. And then finally we had something called the fivefold. So I press to update, and suddenly they draw automatically these things. And the idea is have boxes, you cannot really see here. But these are basically containers, each of them doing their own analysis. Now the goal is, let's try to analyze as much as possible. Let's alt tab to start running a server in the background. Because some of these tabs, they allow to talk to a server. The advantage is that if you use a server, you can actually use a model check automatically without having to copy and paste the files, or you can use constraint solving to decide what to show, which is actually being done. So you start experimenting with this. So this language is actually more powerful. We have some ways of specifying parameters and constraints for the parameters. You can specify a hierarchy of connectors, so this can get more complicated. So let's just shift this online version. Now I'm talking to the server running on the background, if it works. Okay, fantastic. I'll even do some small shifting, which is making sure I change a bit the layout so you can actually see it a bit better. So each of these analysis tools, you can actually collapse them or open them. And here you can see the behavior by moving your mouse over the actions, and you see what's these Christmas lights appearing in the connector, and those explain you what's the possible behavior each time. So if I put here, you see that the possible behavior on the initial state is to have communication from here to there, and also goes inside the fivefold, which is actually over there. So you can start analyzing what's the behavior of the system by looking at the automata, similar to what you saw before, and start investigating how to map actions in automata to events being fired. So this is one of the things that we made. So we did other things. So if you hide this, we can also say, here's a logical property. Is it is it always possible to have a FIFO having some action or that FIFO? And you can actually generate and say, yeah, it's true. Under the hood, what's happening? Under the hood is actually generating this chaotic expression that no one can read. That will look at this. If I look here, this is the code for model checker. So we're basically generating lots of things that go into model checker, and also from that expression generate code from that to generate a logic expression. So the key point is, in all times you need to generate this, and now you need to understand this in order to analyze it. We're trying to hide this as much as possible by making sure that you have a layer that the user, just by understanding this picture, can analyze it, and then under the hood you start adding more and more of these things. So you can analyze time behavior, can analyze other things, and that's what I'm trying to exploit. And the fact that I put here the server running, but if we go, let's see if it works, 194, so something running online already. And now, so here we can also do the same kind. Let's open a more complex example. So the example we saw before was exclusive route, no, it's alternator. So here's the example. We can actually say, yeah, let's verify it. And it says, after exposing some things, it says yes or no. Okay, sorry, this is not the online version, this is the online version. So the key point is that everything runs on the server already. So no one needs to install anything. They need to know the URL, and you can experiment with different semantics, even code generators and so forth. Okay, so let's see if I can spend more time and continue with the talk. Okay, so this is actually something running in JavaScript. I don't usually program JavaScript. I avoid as much as possible. I use something like Scala or something high level that generates JavaScript. So I don't advise anyone to put your hands on JavaScript. It's a bit too messy. But the moment you hide it with the proper language with the hood, it's okay. And then you can actually have sockets running on the background as I do, and then you can use your favorite language to talk to the interface. So semantics. We saw this automata-based model, right? The point is, at some point, this, because it was born in the place that was doing concurrency theory and formal methods, lots of semantics started appearing. So more than there were case studies for it. That's the feeling I have. And this reflects a paper from 2002 by one of the PhD students from Farad. The title is Overview of 30 Semantic Formalisms for Real. So this, in my perspective, shows that there was a bit of an explosion. So these are possible lists that they get categorized. So if someone is a bit more used to Petrinet's structure operating semantics, or in terms of automata, you have lots of different automata that can reason about it. So there's lots and lots of possible extensions. They look at this automata and they say, oh, I don't want automata. I want to reason about logical constraints, or post-algebra, or something based on sets, or something based on strings of time and data side by side. So there's lots of different semantics. If you come from one of these fields or used to them, and you understand what drill is, you can actually jump into a different one. So in the paper, they also have this kind of dependencies of different formalisms and different kinds of semantics. And the good thing about this is the citation. So it's a way of finding the paper you want in case you want to understand a bit more. And there are inclusive more recent ones from 2017, so it's not stopped yet, where they propose using hybrid automata. So this automata that alternate between discrete steps and continuous steps, where you have some differential equations, functions describing your system, and then some jumps that change the system of equations actually being triggers. So there's research, and we can choose based on the case study. So my experience tells me that the interesting part of this is finding first the case study and then adapting your model to make sure you target the case study and not the language itself, because lots of people try to experiment and starting to be a bit too much of a mess, getting just a formalism because of the formalism. So I'm interested to collaborate with anyone who says, I have this that can be translated into a coordination problem, is there a compositional way of building this? And I'm more than happy to try to investigate what can we do. Okay, so I showed most of what drill is. I really hope you got the grasp of what I mean by focusing on interactions rather than actions and extracting the coordination away. I also showed a bit of the analysis tools. So I hope I'm not taking too long. So Patrick, kick me out if it's too much. So I'm going to focus mainly on these two things, which are something more recent. So this timed automata is actually something published also in the Brazilian SDMS or Symposium, Brazilian Symposium in Informal Methods, where we look at timed automata and add something extra. That's the next two slides will be about it. And also the work, our experimentations of using this language in the context of coordinating tasks in a real-time operating system. Because that's something that you might be able to be more familiarized, that's why I focus a bit more on this one. So, IFTA. So a very strange name that means interface feature timed automata. What is this? Well, sure, you start by having automata, the timed automata. So for those who don't know, it's basically a state machine where you have locations. And implicitly you have these special variables that measure the time that passes. So this is like a stopwatch, which means the state reflects not only if you're here or here, but also what does your stopwatch tells you. It passed 2 seconds since my last reset. And every time you do actions, the actions you can do are based on some conditions or some updates. Tells you, hey, you can only go if your stopwatch is more than 2. And you also have some kind of invariance attached to the states. So that tells you you're not allowed to be here if this invariant is broken. So it's a very popular way of specifying behavior that depends on the time that passes. So there are several algorithms that they use actually time that passes to be able to have to implement the algorithm and so forth. So if time influenced behavior is a quite nice model of implementing it. So the first thing we did was let's add variability. So I mentioned variability before. That basically means adding features which can be seen as these special red variables, CF and MK for coffee or milk. So assuming that your coffee machine that you have here, you can brew coffee and take some time to brew coffee. Suddenly you say, wait, we have 2 versions. We have the version that can select the coffee feature or milk feature. These are features that if you select them, you'll generate different codes included on your final product. But in your model also tells you, well, if there's coffee and milk option, then this arrow of cappuccino appears. So your coffee machine now might brew cappuccinos. But depends if you trigger the feature saying I have milk included. Outside the system, you can say some global constraint tells you, yeah, you want milk? Yeah, you want milk only if there's coffee. There's no milk in the machine if you don't have coffee first. So this is the spirit of building variable systems. Making sure that the configurations affect your model. The easiest way is by saying something is present or not based on this feature, based on some expressions. Be able to reason about how they relate to each other. This is the feature model that you have here. And then so basically these representative you can project based on selections of valid features. If you say I'm not interested in having the coffee feature, it tells you okay, no milk, then the cappuccino disappears, everything else maintains. Here's the instance of my possible feature models. So this technique is something also used for code generation. So in C codes you see this if devs quite often it tells you this code will appear there or not. And outside the model you have this set of files that tells you which variables are actually set or not. You can actually reason about this and tells you this is a combination of possible configurations. People from verification do similar things by saying, oh, these are the possible configurations, then let's make sure we only analyze this possible set of configurations and focus on the behavior based on knowing that only coffee or coffee and milk might be present. And ignore the scenario where milk is present but not coffee. So, we have features, we have time machine, we have time automata. Next part is interfaces. With our interfaces, this is basically telling you how to compose things. So if you have this nice coffee machine that you just saw here, it might have coffee, you might have the possibility of cappuccino, we don't know. We saw this might be configurable. And now you have a payment machine that you pay, and my data might allow this button to say option 1, might have option 2 available. But again, you also have variability, because the people building the payment machine, they also say you have multiple variants based on the one you actually prefer. And now you want to to replace this by this one where we actually put the box around and saying these are the interfaces, which basically means I can have coffee, cappuccino, or brew actions. These are these balls here. And the payment machine will have something similar. You have the input of coins, making sure you can actually have option 1 or option 2. Now, everything is translated now into the formal model. So this pretty picture, it's mapped into this one that you saw before, but now we have this box around saying what are the interfaces. The red parts means this interface will only be there if this holds, and it's actually something that you can take from the model. And now you have something a bit ugly as well, but something very usable. It's basically, if you have some input, you can say this will go at the same time as output 1 or output 2 or both like that. So this is a variable machine. This is a variable machine. We compose them together. We know how to build this automata. It's very similar to automata you saw before, but only had actions. Now we just keep adding more things. So just to show you things can get more complicated. So this is not something big. It's something okay for a computer. For a person, look at this, all these red variables, it's just chaotic. But the kind of constraints here are actually something quite simple for a constraint solver to handle. So what you do is we build this system. We use a set solver to be able to say, here are the possible combinations. So these are the possible payment coffee machine you can have. And suddenly we can generate the products and send it to UPAL or somewhere else to verify it. So this we actually implemented as well. So where you saw this picture generating the automata and so forth, a different box was actually for timed automata, and you can actually output a model in timed automata that either has this composed model or these instances, have something automata side by side that actually selects which features are possible after knowing which combinations are possible. So try to show that we can implement this in UPAL to verify it. Either these complicated things or even both of them in parallel, because UPAL supports somehow to do things, to support automata in parallel that communicate with each other, and this can avoid actually some state explosion in some cases. So, experimentations by grabbing this. So, the consequence we have is that this reusable piece helps a lot. So, this was made in the context of a case study for the e-government, where it was actually the problem of what happens if you ask for a document that requires a document and then you go through a different process of the bureaucratic process. You want to make sure there's no deadlocks in this that happens. So everyone has to fight and struggle with paperwork in a country that's not yours. Quite often you realize there are mutual dependencies and you're stuck. And you eventually need to have some handwritten paper saying, I'm temporarily doing this, so you can actually break it. So it was the same, it was the kind of project that she was working on. So there was several of these pieces being built together. If you ever use UPAL, you understand it have two, everything is fine. If you have 5 or 10 of these things, you cannot manage it. It's completely unusable. So this is what I mean by the architecture. So we want to be able to compose this. We have our own language to compose these things, having several of these coordinators, which are these exclusive ORs or duplicators or things that are variable but composable. Now we build an architecture full of these pieces where some of them are automata and handwritten, but lots of them are just reusable pieces, and then you can still analyze it. So we have examples with a bit more examples that we can actually check and verify properties. Okay, this time automata. Is there any question? For 5 minutes, right? Yeah, I see. So, 2 slides for here now. The other case study was real-time operating system. So what we had is, so there's a project I'm leading now, and what the initial partner is Alshon. It's a company that is hosted in Belgium, it is very small one. But they have the operating system running, they call it Virtuoso Next. And they also have infrastructure, so they have their own IDE, so where you can specify which nodes they're actually being deployed. And you can also specify the behavior, so you have the visual interface where you say, here's a C program for this task. There's another C program for this task. They are both running in node 1. And at some you draw these things, and these are not tests anymore, it's not C code anymore. These are the representation of semaphores that will be interpreted by a kernel tasks, some task that's running by operating system and deployed in every node that you actually deploy. So their own system knows how to interpret what the semaphore is. And what it does is, this task will run until they try to interact with these semaphores or with these special entities. There, they go out of the scheduler. The main task decides what to do next based on these constraints, and then tells you, okay, now you can go because based on who can go next, that shows that one. So this is different from scheduling. This is actually deciding the behavior of the system, who can go next. It might involve some data buffering, so you might need to store data temporarily before actually allowing someone else to go. And then when they execute this, because they are a real-time operating system, they are able to compile with a very big precision what's running on the board they're actually running. So that's their selling point, to make sure that with the precision that goes to microsections as you need. They log the minimum amount of possible to make sure it doesn't disturb your system, and you can still understand what task 1 and task 2 are doing, how much time they spent, and this kernel task that is actually interpreting these semaphores, how they evolve. So what's our contribution? Our contribution was in the center part. So in this example, you saw this was C code, and these are hubs. That's what they call them. So we look at these hubs, and they said, well, based on our clients, we specified 5, 10, 15 different ones, fixed ones, make sure you can verify them. So these are the ones you can use. So the clients, when they're programming and trying to coordinate them somehow, so specify this kind of glue language that we talked before, they have this palette of available options. And the question we raised was, so we look at the code and we realize that lots of the behavior of this coordination was still inside the tasks. Why? Because they're not expressive enough. They're very simple. They are very good to hold and send data. Something more complicated, like you're alternating behavior between two, you still need to put inside the programs. So what we did in this task was trying to investigate how to increase the expressivity of these hubs. So this is the published work is not yet accepted. First of all, is what you like and love is to get these small things and first formalize them. If you look at the papers they published, they say the list of each of them, and basically they have 1, 2, 3 paragraphs explaining by text what can happen, which is something you need to understand how the underlying system works to understand the actual behavior. So you start by formalizing using some kind of automata saying, here are the restrictions, here are the state updates, this is what can happen. And finally, we tell you how to build more complex hubs. We use a bit more of our own, set duplicate and so forth, and tell you, yeah, if you have 2 tasks in the actuator, you can draw these complex things. We know how to generate the automata for these kind of things the same way as you used to. This is a special one that handles data updates and data constraints. So something that looks like C code that you can map into C code easily. And tell you that, okay, this is easy to analyze and simulate. They were very scared by saying, no, it's not efficient. Look how many ones we have. We don't want to run this because we know how the old ones work and they are very small and efficient. This will just break efficiency. So our claim is that these complex things will actually go to a 2-state machine. So we can measure how many variables we need, how many states we need. So we just need to be able to implement this small, tiny machine which you can analyze and verify. So again, we're not deploying all this. Where we're actually deploying, ideally, is the automata and the underlying semantics. So this is something submitted. We're investigating now is how do you go into the communication level between nodes. So this works at application level. You have tasks and application level that restrict their behavior inside the same node. If you want between nodes, you want to have symmetric control of what is the protocol to make sure using whatever communication layer network you're using, how to make sure you can juggle it better. So that's it. Just wrap up. Coordination, time automata, and real-time automatic systems data. 2 of the research tracks I showed you. And something I'm also working on now is the concept of graphic programming for the IoT. So also got the paper accepted and I'm trying to push a bit more, which is also composing boxes, but different kind of boxes. Logics, what's the best kind of logic? And I say here dynamic logics, so logic based not only on states, but on actions. So if you know UPAL, this CTL, LTL, they basically constraints where you can have some modalities saying about the time, the future exists, doesn't exist. And the properties is about the state. I mean the state where I have that location or the variable x is set to 5. This one talks about action that can occur, not on state but on actions. And finally, I'm working on also an hybrid program, so languages to talk about these systems that are continuously behaving. So you have a function that tells you, now the speed of the car is slowing down. At some point, I'll update my cruise control, and now I'll change it, make sure the station goes up, because it reaches a certain condition. How do I specify the system using a language that combines continuous and discrete behavior? So, that's it. Thank you.
Thank you very much for the talk. We have room for a few questions.
If your framework or this type of language is good for coordination between different entities, can it be used in another context, like for example securities, or like identify threats or misbehavior of one of the entities? Is that possible, or is it a bit too crazy?
You can do it. So the thing I have, so the key idea is that you can try to replace these channels and say some of them guarantee some kind of security properties. Now the key challenge will be saying, first of all, once you map to the semantics, what kind of language you want to use. And there are languages talk about the security using kind of calculus. There's the spy calculus and other calculus that focus on security. So you can do that. My feeling is that most of the challenges, and there are a lot of challenges, are not associated to this, but are often associated to side channel attacks and then kind of attacks that it's very hard to capture in the model.
Okay.
So my feeling is that the challenge that will come up will not be so much on how to specify and build a connector, but how to, after you enter in your semantic model, how to reason inside. And that's a full community that handles this, and it's not easy task. So it could work at the top level, but the hard part, I think, will still be on the low level once you have your semantic model, how to actually reason about it. You can try to outsource for existing tools, but it's not clear how much you still need to understand in order to make sure this system works.
Okay.
Even for specifying, not so much looking at, let's say, how an attack can be accomplished there, but more in the sense of using your language to define some security protocol. I think that would fit more in an interaction-based language where you have some sort of automatic reason underneath. Looking at that perspective, I mean, I designed my own protocol. I want to do some quick checking on it. I don't want to do proofs by hand. Would it make sense to try to extend your iteration models? The question is a bit different from what Ramiro said. So maybe in that sense could be easier.
So the question I think is, the moment you have actions, if you start attaching security-related aspects to the actions.
With your actions, you have imagine an action that carries some sort of key and you want to reach an agreement, something like that.
So it could work. So the point is that you want to verify properties. The properties quite often here are saying, these are the possible sequence of actions you might want. You need to extend this logic by saying, these are the sequence of possible behavior, knowing that the action has some kind of key, signature, something associated to it, and then you need to understand exactly which model you're able to verify it. So that will be the difficult challenge.
This to some sort of secure by calculus or something like that.
So it could work in it.
Yeah, because any security solution in the end is restricted to the variables that you have at hand, because there's always some out of band attack that you cannot control. Or,
That's what I mean by such an attack.
Yes,
So
yes,
it's
yes.
very often there's something that's not part of your model. So usually the people working in security, they say, here are either the validity threats or the assumptions in the front.
Yes, yes.
And if these might be too strong for most people from the community to accept this, so the challenge will be able to say, the assumptions we make, they are acceptable because we can still verify very useful things under these assumptions. So this will probably be the first step you have to make to make it useful. But indeed, my main concern is we might jump into the challenge that is not the architectural challenge, but actually the challenge of the different domain. But you might be able still to get protocols that will be able to reason and say, oh, it's not secure, let's just rewire. Now it's secure by rewiring. So
yes,
if this is possible, this would be great. Yeah.
Do you think about to put some symbols for debugging also?
Symbols for debugging.
Yes, for I don't see a watchdog that you put in your connector.
Okay, so debugging can have multiple ways of multiple meanings. So debugging could say, how can I make sure that my connector is okay? Let's try to run and see if everything is fine. Or debugging might actually see, let's look at the generated code and see if the code is happening with the code generated code and see if it actually matches what is there. So if you look at debugging by saying, let's understand what the code's, what's happening there. So quite often what you want is to be able to simulate or to have some intuition about linking what your system is to your semantics. So that's one of the challenges we try to address, to make sure you can somehow bridge the two, because sometimes it's a bit tricky. You lose information once you go to the semantic model, and trace it back to the connectors quite often is a bit tricky. So I don't know what else I can tell about debugging. So to help the code developer to debug their own code.
To help the code developer. So I don't know if it put some extra options to see that your code is run correctly, and sometimes you have to help to test and verify if your code is correct.
Okay, so now we can generate can generate codes. What you can often do is to check if the program is correct. What you do is specify properties. That means this is what the other requirements is what means to be correct. And then you try to check those requirements or those rules against the semantic model. That's the most common. We try to avoid going into the world of the generative code, because it's much easier to handle things at a high level. If you want to look at a low level code generated, you usually want to make sure that it's hand to hand with the model you have. So the challenge is how faithful it is. It's something else that can happen in my generative code. It's not happening in my model. So I would split this challenge into these two ways. First, making sure that your system or semantic is rich enough for the kind of requirements you want to talk about. So whatever your requirements address, make sure your model includes them. And then once you generate code, you avoid rechecking those things, but you make sure that the model you generate is faithful to the one you have there. Just make sure that you have a correct system by constructions as opposed to generate constraints. Of course, it's also possible to, in a world that has failures, and you cannot really check the failures up front because there are too many causes of problems in your system. You might want to use your requirements also to generate something else, like monitors or extra constraints. So this is something that's fully open for research. We didn't experiment this because we assume that our world is this world. Once you generate code, you're out of our comfort area and we avoid touching it. But there's room for checking something there, of course. Yeah.
Has already been any effort, or if there is an advantage, interest that you see on actually formalizing this in a stronger formal method, like the one supporting material improvement? In the sense that you would have a broader, more expressive framework to reason about any other construction that you would like to add to your basic model, let's say.
So if there's...
Trying to encode this, for instance, in Conc Isabel or something like that. Was there any effort, and do you see any kind of advantage?
Well, there's always advantage in trying to encode this into a different framework.
Mm-hmm.
So the first thing you say, your framework, what are the good things about it?
Mm-hmm.
Okay, so there's these good things, so it's worse. So right now I have students working on encoding to alloy, which is the other one. The good thing about it is that the description starts by very abstract and you keep adding more complicated things, so it's very good to experiment by how to extend small things to the model I generate. But I only see advantages there if for someone who understands Conc for the time being. If you want to exploit the solver it has, I think there are other ones which are much more efficient if you want to hide away in the hood. So right now we also use MCL2, which is something developed at Eindhoven University, which is very efficient for large state spaces. So there we focus on these dynamic logics, on these actions that can verify. So we are experimenting with different ones. And if there's a framework which is very good at something, typically there's advantage in doing it.
Because from my perspective, well, you are saying that you are using those two tools, but those two tools do not provide an essential thing, which is actually proof that things are okay.
Yes. So more or less. So we try to give right now. This approach is model checking based.
Yeah, so they can give you counterexamples.
Which is a bit weaker than verified.
Yes. So this is a question that I put every day. I really enjoy this kind of stuff, and I did my PhD using a field improver. And one of my conclusions is that when you put yourself available to encode already a complex mathematical model in a broader one, is it really worth it? So that's my question. Here, what I see as a big advantage, I'm not sure if you agree or not, is that if I encode in Calc, define the basic specifications, the core ones.
But there's already work that encodes connectors using some kind of semantics into Calc. So using basically data and...
That's why I'm asking.
Yeah, so this exists.
Okay.
So what's the purpose? Was to be able to show, is this connector the same behavior as this one? You want to formally prove that that's the case. So they use Calc proofs, very manual ones, and there are some experiments trying to use machine learning to automatize the statics to be able to be, but it's because it was very specific proofs. But I don't think it was satisfactory result in the end. So these are basically a group in China. So there was someone that also worked with us before, both in Mingo and in CWI, and now he's a professor in China, in Beijing. So there's some of them. So the advantages. So also the Father Bach in recent presentations, he tries to sell advantages as code generators. So there are some experiments to generate code from here into low-level C code with shared memory, which he claims they can be as efficient or sometimes even more sometimes than the handwritten code to make sure this works. And this for me is a very big plus, saying that this looks very high level with the potential of exploding states. If in the end you can generate code that is as efficient as someone who really understands the under the hood and still be able to have the high level of flexibility, then you have the advantage. Because you can still change, modify, adapt, and don't need to struggle in the end to do this final optimization.
But you are talking about a special purpose tailored code generator.
Yes.
Okay. And
so the message here is which abstraction level should be used in the value. If you can keep it high enough, the problem high enough sometimes that you lose information that is used to optimize. If you can actually derive optimal enough, it means okay, then you should be as high as possible, because that's where it allows you to change the protocol, change things more easily without breaking things.
So we will now give an hint of something that is really interesting, I suppose, is that instead of crafting your own code generator, why not encode this in Calc and make Calc extract correct code?
Yeah, we can do that. So
it will not extract C, so it extracts only to OCaml or Haskell, but then there is another work by a guy in the US whose name I'm now forgetting, which provides well-defined and methodological way to transform functional original ML code into C code or imperative code. So if you encode these two components, what you will end up doing is providing a foolproof code generator. That will obviously blow people's minds because it will take a lot, and again I'm not sure if it's worth it, but it's clearly a path.
So this might be a path to be able to generate certified code, right? Yeah. That's the key point.
At least some code that you can present to the certification authority and say, okay, you can look into it, but trust me, it is correct.
Okay, so key advantage might be performance, right? You might lose lots of performance if each of these parts are not seen as a whole composed behavior that's actually running, but if they are seen as different parts that are talking to each other.
Yeah.
It's very likely in the final end, the semantics of the program running will still have the small parts talking to each other. And it will be extremely inefficient. So part of my PhD was also looking at this thing and saying, how can you avoid having one single automata? How can you spread this thing and guarantee the semantics equivalent? So the challenge of generating efficient code, distributing code, and so forth, it exists, not clear. It depends on scenario to scenario, or even connector to connector, what's more efficient. And by this, you very likely lose performance. At advantage, maybe if you can show, so you might gain if you want to be able to have multiple copies saying one certified, one non-certified, to make sure that you can simulate and understand and only then use efficient punishment.
And you can even tweak the formalization so that you extract not only code but interfaces to libraries that exist and that may give you some, because you can extract complete code that compiles by itself, but you can extract only the headers, and then you just link in the compilation process with standard libraries from OCaml or something like that, so you can get that.
Okay.
Okay.
Yeah, so the challenge will be to motivate and saying it's useful to have generated code.
Yeah.
That will be the, I think, so maybe if you tweak enough the semantic and saying this will be complex to do otherwise,
Yeah.
then you'll have an advantage. Otherwise, people will say, no, it's too simple.
And you can always have, let's say, a canonic code generation mechanism that you can always build another one and prove that they are equivalent. So you always have that.
Because here the advantage of selling is flexibility.
Yeah.
Easy to reconfigure and change.
Mm-hmm.
Easier than if the code is somehow mangled at low level. Thanks.
Last question.
So can we use this coordination language between heterogeneous agents or just between homogeneous agents?
So what you're trying to sell without really showing off results is saying this entity component stage could be in any language, any world. The important thing is that they have some kind of interface or contract to make sure that whatever we built here knows how to interact. So it's this black box approach. Computation should be completely separated from here. It doesn't mean in practice it's easy to achieve. Quite often there are lots of assumptions you need to add for this to work. But yeah, the goal is that. Make sure you don't rely on everything being running on the same protocol, same model, because you want to have a different language. So this can be Java, C, OCaml, whatever you want. But this one can be communicating via IP sockets or via foreign function interface or something that actually links. So you just have to make sure you can reach it, and you want to have your own language to talk about this. And avoiding handling computations there. That's the principle. But okay, again, now it depends on the computation.
Muito obrigado.